All right, so today I was asked a question about problem 6.35, and this one actually gave me a little bit to think about because really it's not as obvious as you might at first think. 6.35 on the homework says that you have a spring and it's got a spring constant of whatever. And my spring constant is 56 newtons per meter. And what that means is that every meter that you stretch, it's going to take 56 newtons, or if you apply 56 newtons to it, it stretches a meter. So we've got this unstretched spring, and it says the end of the spring is next to the 18 centimeter mark on a ruler. So you guys did the spring lab, and that's 18 centimeters right there, or 0.18 meters if we're going to change up the units since that has meters. It says that you're going to have this spring and it's unstretched there, so we're going to put on a mass of 3 kilograms, and that mass is going to stretch it down. Now, the big issue with this problem, I think, is what people are thinking about it. They're thinking that when they put this mass on it, it's going to stretch. It's going to stretch the spring, definitely. But they think that whenever the force of the mass, which is on the free body diagram, whenever the force of gravity is equal and opposite to the force of the spring, then we're done. That's what we're looking for. And I think this is what kind of threw me for a loop today because you guys were doing all your Rube Goldberg projects and I was having these questions, so I didn't really get to think about it properly, or actually read the problem all the way through, which is I guess my fault. But whenever the force of gravity is equal to the force of the spring, yeah, there's no more acceleration here at that point. But think about what happens if you put a mass on there. That spring is going to be moving downward. It's going to be pulled downwards. And at this point, whenever this force becomes great enough to counter the force of the spring, it's moving at its fastest at that point, which means it's still moving down. And the question says, what is the position of the ruler, or of the spring on the ruler whenever it's at its lowest position? So really, at this point, it's still moving. So it's going to move down here. So this problem's a little tricky whenever you think about it, because at first glance, you might think, oh, well, I just need to set kx, this force of the spring, equal to mg. And you would do that if you wanted to find out, if this thing was allowed to just keep on going up and down and up and down and up and down and just come to rest. Yeah, that's where it would be. But whenever you first put that mass on there, it's going to stretch the spring to here and then keep on stretching it down to here because it's still moving at this point. So that's where it really stops. That's the lowest position. And that's going to change how you solve the problem. So in order to do this, we're actually going to look at energy. So if you first solve this problem, you're looking at energy, we're looking at changes of height. So right here, we have some kind of change of height, some h, let's call it h1. And this is really the one that we're concerned with, this h2, okay? And I could go through and prove to you that if we just solve for this change of height and we say, hey, what's this change of height equal to? That's going to be some kind of mgh change. And all this potential energy, because of this h1 change of height, that's going to go into the energy of the spring. And if you figured out the energy of the spring, 1/2 kx squared, based upon that same h, that h is actually x, you're going to get two different numbers here. And it's true. You should get two different numbers there because the change of energy, the change of potential energy from 0 or 18 centimeters down to whatever the height this is, that's not all going to the spring. That's actually going to the kinetic energy of the object. So that's why this one doesn't work out. All right, so what we're really looking for is this right here, this h2. So from here at 18 centimeters all the way down to whatever this is, that's our actual change of height that we're concerned with. So really, we're losing this much potential energy. That's going straight into kinetic energy, but it's being taken out again by this spring. So right here, just understand what's going on. We have an object, we place it on spring, it stretches it. At this point, it's still moving, turning all that potential energy into kinetic energy, and some of it's going to the spring, but then we still want to figure out where it stops all the way down here. So all this potential energy is being converted into the energy of the spring. That's why this is an energy problem. And so really, these two things, all this mgh2, all that should go straight into the energy of the spring. That's why we're going to set these equal to each other. So mgh2 is equal to 1/2 kx squared. Now I'm going to do one more thing. We got to realize that this x is the distance that this spring is stretched or compressed. And if it starts off here uncompressed, h2 is actually x. So that goes in right here, and this actually makes the math a heck of a lot easier. I almost wrote there you go. H2 squared. Okay, so if we have an H2 over there and we have an H2 over there, we have two of them over here, we can just divide both sides by H2. And here's what we're going to get. Mg equals 1/2 K H2 on the right side. And this allows me to solve for this change in height now. So move the 2 over, I have 2 mg divided by k, do some math, and that's going to be equal to my h, my whatever this change in height is, this drop. So plug in my numbers. My mass was 3, I believe. Yeah, it was 3. And that's going to be times 9.8 because this is mastering physics, not the classroom. You know, we do things with 10 to make it faster. K value is going to be 56, and that's going to give me h. Let me pull out my calculator, see what that is. Let's see, 2 times 3 is 6, times 9.8 divided by 56, and I get 1.05. So 1.05 is my change in height, meters. And remember that we start off at 18 centimeters, so really I'm just going to add my 18 to that, and that should be my answer. So hopefully that helps out. Hopefully you guys find this in time. Homework's due tomorrow. Thank you.